Welcome to the glass plate. In this example we're going to take a look at energy and energy transforms. Let's consider a very simple basic system. We have a mass m of 10 kg that we drop from a certain height to the floor. Initially this mass has zero velocity and thus no kinetic energy, but it does have potential energy as it has a height h lifted above the ground. In the example we're going to compute what the velocity will be when it reaches the floor via an energy consideration. Initially there is potential energy of mgh, and that will be converted into kinetic energy. And that kinetic energy will be found here, velocity v, just before impacting. Energy conservation says that the energy here must be the energy there, and thus mgh equals half mv squared. This is obviously a simplification, as we ignore any frictional effects when our mass comes down. But if we do so, we see that we can scratch out the mass, and then we can solve easily for the velocity. V will be 2g times the height square root out of it, which if you take, for instance, 100 meters, will give you about 44 meters a second. Once our mass reaches the ground, it will bounce up and down a few times and then lay still. And the question we could ask ourselves, what happens to the kinetic energy that it came in with? And the answer is it turns up into heat. So eventually that becomes heat. We're going to assume that all this heat will be inside our mass, that nothing is lost to the environment. Again, it's a simplification, but it gives us an idea, a feeling of what happens to this kinetic energy that came out of potential energy. Thus we say that all energy is now found in the form of internal energy, a change in the internal energy, and the temperature will thus change, and that is equal to all the energy that the particle had upon impact. So all the kinetic energy is converted into heat. Again, we can scratch out the mass, and if you look this up, then you see that delta T is about v squared over 2cp, and if you put in some numbers, we take a Cp specific heat of 2500 joule per kilogram Kelvin. This is 0.4 degrees. And what you see is that the temperature rise is very small. But it doesn't mean that the energy involved is very small. That is still the original half mv squared, which is still the real original mgh, 100 meter lifting. It only says that internal energies reflect themselves with normal mechanical energies as very small temperature increases. You can store an awful lot of heat inside a particle, inside a mass, before it really changes its temperature. But the temperature here is the measure of the energy. And what we see is that we came from potential energy, the particle is lifted up high, that is turned into kinetic energy due to the action of gravity when it falls down. After the bouncing, everything is heat, and we computed what that means to the temperature of the particle, if all heat is stored as internal energy in the particle. In the next case, we're going to consider a little bit of a fuel. So here I got a drop, and that drop, say 1 gram, can be burned in essence. The chemical energy stored can be freed, and if we do so, it will release 45 kilojoules of energy. Suppose, and I call this the energy of combustion. When this small drop of petrol, when I combust it, this amount of energy is released for that 1 gram. I could think, okay, suppose I could turn that all into kinetic energy. How fast would this drop then move? The drop doesn't exist anymore, I burned it, but I give you a feeling for the numbers. And that is easy, because now these two are the same. I use conservation of energy, and I, in my mind, think that all this combustion energy is converted into kinetic energy of the particle. Thus I can compute V as the square root out of 2 times the combustion energy over the mass of the particle. And that is a staggering 10,000 meters a second, showing that chemical engineering stored in ordinary material, like a drop of petrol, is enormous. It is very difficult to get the same amount of energy in terms of kinetic energy and their velocity. Chemical bonds contain an awful lot of energy. Sure, we could also compute, suppose we don't use it for kinetic energy, but we use it to lift up this particle, so I turn it into potential energy. I bring it up rather than up to speed in height. mgh, and the question is, what would be this h? Well, the same energy conservation will tell us that h becomes the combustion energy that is available to lift divided by mg, which is again an enormous number, 4,500 kilometers above the Earth. You're quite a bit outside our atmosphere. Basically, this particle is now floating somewhere in space. Summing up what I used, combustion energy can in principle be converted into kinetic energy or in potential energy, and we see that if you do a little bit of calculation, chemical energies are very, very high, much higher than potential kinetic energies that we are used to.